Transformer differential protection has one of the hardest jobs in the substation. Stay perfectly stable through load and external faults, operate fast for an internal fault, and refuse to be fooled by magnetizing inrush or overexcitation. This workspace proves a real relay does exactly that, and everything you're about to see is driven from the relay's own manual-backed settings. First, pick your relay because all 4 families are modeled end-to-end. The GE and Schneider MiCOM P632 family, ABB's RET and Reg on the Rec 640, the Siemens 7UT, and the SEL-787. Every setting name on the rail comes straight from that relay's own manual. Today, the 787 is our star. The scheme itself, a 90 MVA transformer, 132 over 33 kV. The HV winding is star, clock 0. The LV is delta, clock 9. HVCTs are 400 to 1, LVCTs 2000 to 1. The relay has to line all of that up before it can compare a single amp. And look how deep the input rail goes. Each winding carries its own connection, earthing and clock position, along with CT ratio, polarity, and correction factor. Below that sits zero sequence filtering and a live injection section where every phase current, angle, and harmonic percentage is yours to control. This is a complete scheme description and behavior validation workspace. The group settings load as the factory defaults from the 787 manual. Minimum pickup, 087p at 0.3. A first slope of 25% rising to 70 past the break at 6, an unrestrained pickup at 10, and second and fourth harmonic thresholds of 15%, with the fifth at 35 and harmonic restraint enabled. Nothing invented, nothing tuned to flatter the demo. So let's apply the through-load case, where a healthy relay must simply sit still. Restraint reads 2.0, giving an operating threshold of 0.5, and the differential current is 0. The vector group rotation and zero sequence filtering line the star and delta windings up so the currents cancel exactly, resulting in a stable scheme. Here's the characteristic doing that work. The operating point sits on the floor of the restraint region, hard against the axis. Everything that follows lands somewhere on this dual slope. And before anyone assumes this is preset wear, watch. Every value on the rail is yours to set. Take the first slope from 25 to 40% and the characteristic steepens in front of you, leaving the ghost of the old curve behind for comparison. It's your relay, your settings, and your scheme. Let's put it back to factory and carry on. Now let's apply an internal fault. Both operate and restraint read 4.382, one-sided in feed straight into the zone. Below the slope break, the threshold is 25% of restraint, 1.096, and the operating point lands miles above the slope, resulting in a biased differential trip. Next, the external fault, and this is where schemes get found out. Heavy through current pushes restraint to 16.26, well past the slope break, so the threshold rides the steep second slope up to 8.68. The compensated currents still cancel, and even a real CT error spilling current would need to beat that raised threshold. Internal trips, external restraints. The dual slope is the whole job. And the verdict rail doesn't just give you the answer, it shows it's working. The overall verdict up top, compact response cards for each phase, then a detailed ledger with the differential, the restraint, the threshold, the margin, and the decision path, and finally a proving assessment confirming the case did what it claimed. Every number you'd want to check is right there. Now for the false trips. Energize the transformer and magnetizing inrush pours differential current into the relay, 1.35 per unit here, with no fault anywhere. The tell is second harmonic, 45%, 3 times the 15% threshold. Watch what the 787 does. Harmonic restraint hoists the operating threshold to 4.38 and the element rides through, resulting in a warning, not a trip. Overexcitation is the same trick on the fifth harmonic. A full per unit of differential current, but 40% fifth harmonic against the 35% threshold. so the fifth harmonic block holds it. Two large differential currents both correctly refused on harmonic content. Finally, let's look at an earth fault near the star point. The phase differential barely registers, 0.1 against a pickup of 0.3, so it does not operate, and on its own it would miss the fault entirely. But the 787 sequence directional restricted earth fault element is watching the neutral CT. Operate current 0.8 against a threshold of 0.1, and it trips. The restricted earth fault catches exactly what the phase element misses. That companion element is why you fit it. One thing to be straight about, this is a vendor-faithful proving and interpretation workspace, built on manual-backed settings and the relay's real decision logic. It is not the vendor's configuration software, and it does not replace commissioning or a protection study. Pick your relay from all four families, set your scheme with your own values, and watch every proving case resolve on the actual characteristic. The link is in the description. Run your own studies and put it to the test yourself at eiportal.com.